Electricity is one of those topics that people find difficult because the concepts are fairly tricky, but the questions can be even harder. But once you break the code with electricity questions, you'll realize that they're all very similar. You just need to follow a few simple rules, and then it's just like a bit of a puzzle, bit like a Sudoku. So, essentially, it all comes down to V equals IR, Ohm's law. So we use V equals IR, however, we could also use the power equation, P equals IV, or its alternatives, to find out something for one component, and then we say this will be true for another component. This will be true for another part of the circuit. That's all that it involves. Let's have a look, shall we? Here we have a battery or a cell. They both do the same job. And this is a 6-volt battery. This is a 10 ohm resistor, and I can tell you the PD across it, the voltage, is 2 volts. So what can we find out about this second component, this second resistor? Well, firstly, we need to find out one more thing about this first resistor. We have V and we have R. What can we find out about this resistor then? We can find out the current. Of course, for that, we can use V equals IR, rearrange it. Therefore, that's what this really does mean. Current is equal to V divided by R. So that's equal to 2 divided by 10. And that gives us 0.2 amps. Now, that's fairly easy, but then it's the rules that people forget. What do we know is true for this circuit? It is a series circuit, and so we say that if that's the case, current is the same everywhere. So can you see? We found out something about the first component, and now we can say that's also true for the second component here. There is one more thing we can say is true for a series circuit, and that is that total V, total voltage, is shared. So therefore, if I know I have 6 volts available altogether, but 2 volts is being used to apply the first resistor, then that must mean that there's 4 volts available for the second resistor there. So I now have V, and I have I for this second resistor. What can I find out? I can find out the resistance. Rearrange Ohm's law again. R is equal to V over I in this case. So that's equal to 4 divided by 0.2. And that gives us 20 ohms. Now, you might well have been able to predict that that was going to be the case just looking at the numbers, but it's not always nice numbers like that. And so these rules are super important. Knowing these rules will allow you to say, I found out something for one component, I can therefore use that for another component. In this case, it was the current that was the same for both. Let's look at another circuit. Of course, you can probably see that I'm going to be drawing a parallel circuit here. Let's say the total voltage is 10 volts. And I know the total current going through the circuit, going through the battery, through the cell, they might say as well, is 0.5 amps. And I can tell you that this resistor here is 50 ohms. I can tell you that this resistor here is 30 ohms. So it looks like we haven't really been given that much information here, but there's still some things that we can infer. Let's have a look. We know this is a parallel circuit. So if that's the case, we know that V is the same for all branches. Then if we have 10 volts available altogether, that means we must have 10 volts across here and 10 volts across this resistor too. Cool, now we're getting somewhere. Let's look at the bottom resistor. We know two things, 10 volts and 30 ohms. We can of course find out the current. The current is going to be equal to V divided by R, rearranging Ohm's law again. So that's equal to 10 divided by 30. And that gives me, well, let's just say 0.33 amps. So now I know that there's a current of 0.33 amps going through the bottom branch. But if I know that I have the total current of this circuit as 0.5 amps, well, Kirchhoff's first law, if you want to know the name of the law that we use, but well, you should know that current just doesn't disappear once it goes through branches. If there's 0.5 amps altogether, but 0.33 is going down the bottom branch, that means that one take away the other, there should be 0.17 amps going through this top branch here. Now I have just realized that technically I've drawn my cell the wrong way around, but we're not too fussed about that. There we go. Current always goes from the long end to the short end. That's positive to negative. Not that it matters too much when we're doing calculations. Therefore, I now know two things about this top resistor here. I can do resistance is equal to V divided by I. So that's 10 divided by 0.17. And that gives me 59 ohms. So there we go. Again, it was all thanks to this rule here. Parallel, V is the same for all branches. Then, of course, we use the other rule as well. current is always conserved at junctions. In other words, whatever current goes into a junction here, we have to have the same amount coming out altogether. Of course, you might have to use power instead. Maybe you're given the power dissipated in watts for a resistor, and that's equal to IV. But we can replace I and V with Ohm's law. We saw that Ohm's law says that V is equal to IR. So if we replace V with IR, we end up with, well, I times R, so I squared R. We can also replace I with V over R. So we end up with V squared over R. So again, you just have to know two of these things in order to find out the third. If you know I and V, you know P. If you know I and R, you can calculate P. If you know V and R, you can also calculate P. An example of this would be transformers, where we have a primary coil and then a secondary coil. This looks like a step-down transformer, doesn't it? You might have something that says, hey, here's a bulb on the secondary coil here, and its power is equal to 20 watts. And the current going through it is, I'm calling it I2 because this is a secondary coil, this is the primary coil, so 1 and 2. The current going through it is 0.1 amps. So if that's the case, then we can of course use just this version of the power equation. We can say that V is equal to P divided by I, so that's 20 divided by 0.1, and that gives us 200 volts. That is a beastie bulb. So if that's the case, then you can just say that. Here's our AC source there. By the way, transformers are just for triple science and A-level physics. If it's 100% efficient, well, we can say the power going in is equal to the power coming out. So we can say power 1 is equal to 20 watts. And then we can go from there as well. We can do our ratio of turns, etc., etc. Point is, sometimes we're expected to use the power equation to find out V or I for a component. Now, you remember I said V equals IR. I mean, that is true for a component, but it's also true for a whole circuit. So actually, it's useful remembering that V total is equal to I total times R total for a whole circuit, or like a branch or something like that. Point is, you can use Ohm's law for a certain aspect of a circuit, not just an individual component. So if I have two resistors in series, these are 50 ohms and 150 ohms. Let's say I have a battery that's 12 volts. Then what can I find out about this? I can say that for series, total resistance is just equal to R1 plus R2 plus R3, whatever, however many resistances you have in series. So therefore, in this case, it's going to be 50 plus 150, that's 200 ohms. Therefore, I can say that V tot is equal to I tot times by R tot. Therefore, the total current is equal to the total voltage divided by the total resistance. So it's going to be 12 divided by 200. That's going to give me 0.06 amps. So if you're stuck looking at an individual component, if you don't have two things out of VI and R for a component, look at the whole circuit. See if you can find out the total resistance. A little bit trickier when it comes to parallel circuits. How do we find out the total resistance in this case? We have an equation for it. Let's derive it real quick, shall we? Why not? We said earlier, thanks to Kirchhoff's first law, however you pronounce it, I total going in is equal to, well, the two currents that are going through the two branches added up together. So we can say I tot is equal to I1 plus I2. Of course, we know that from Ohm's law, I is equal to V over R. So we can just replace this with V tot over R tot is equal to V1 over R1 plus V2 over R2. All I've done is replaced my currents with V over R's for the individual resistors and the whole circuit. What do we know is true for voltages in a parallel circuit? We know they are the same. So actually, let's say the total voltage is 6. It's going to be 6 for that, 6 for that. So actually, they all cancel out. So therefore, our equation for total resistance is 1 over R total is equal to 1 over R1 plus 1 over R2, etc., etc. We add however many resistors we have in parallel. People get a little bit confused with this one, so let's have a go with some numbers. Let's say that this is 4 ohms and this is 6 ohms. Therefore, 1 over R total is going to be equal to 1 over 4 plus 1 over 6. What do we do with that? Well, let's find a common denominator, shall we? Well, 4 and 6, so let's go for 12. So this is equal to 3 twelfths plus 2 twelfths plus 2 twelfths, and so that gives us 5 twelfths. That's not our answer though, because that's 1 over that. So therefore, all we have to do is flip it on its head. So R total is just reciprocal is equal to 12 over 5. And so that's 2.4 ohms. So that's how you find total resistance for a parallel circuit. You can then, of course, use that to find out total current or total voltage as well, depending on what the question is asking. So there we go. That's the basis of pretty much all electricity questions, even things like internal resistance and EMF. After all, that's just 2 resistors in series. It just so happens that one of the resistors is inside the battery, as it were. It's all about just keeping your head, just looking at, do you have 2 things for a component or the whole circuit? If so, then you can find out the third. Chances are you're going to use that third thing and then do a second calculation. That's usually how it goes. So I hope you found that helpful. If you did, please leave a like. If you want to have a look at my big electricity video, then click on the card. Very helpful video. Thanks for watching. See you next time.